Joel, tell me about calorimetry.
Calorimetry is determining the enthalpy of a reaction.
Good. The goal is to measure enthalpy, triangle H. Restart, tell me what a calorimeter is. Restart, calorimeter.
Yeah.
So a calorimeter is an instrument that's used to measure enthalpy, right? That's literally what it is. It's the instrument that we use in calorimetry to actually measure the enthalpy. Now, Gerald, what was a typical setup for the calorimeter that you might have done in year 11?
So you would have a thermometer sticking inside an insulated cup, and there would be water or some other substance which you could measure the temperature change of during the reaction.
Good, exactly, right? So the perfect setup is right here, right? So we have a volume of water that is going to be absorbing any heat change that occurs due to the reaction. So imagine we drop substance A and B, settles right to the center of the solution, and we have a chemical reaction occurring. And that reaction is going to either absorb heat or it's going to release heat and thus change the temperature of the water. Does everyone agree? Now we can measure the temperature change using a thermometer that's being stuck in right here. And we can use that and the mass of the water to determine the enthalpy change of reaction. Okay, so what are the two equations we need to measure enthalpy change? So enthalpy change equals to negative Q on A. You might have seen that before. There is a formula for Q. What is Q equal to?
Q is equal to
You've seen MCAT? Have you heard of Q equals to
yeah,
MCAT?
MCAT, yeah. I have to look back at that.
So Q refers to the energy that is absorbed or released by the water, right? So the energy change of the body of water. So we need the mass of water. Does everyone see that? We need the mass of water here. Could be 200 grams, 100 grams, etc. So this is the mass of water in grams. What is C, Gerald? Do you want to define what C is?
That's the specific heat capacity of that substance.
Good. And what does that mean?
It's the amount of energy required per mole to change the temperature of that substance by 1 Kelvin.
Is it per mole?
The
unit is joules per gram per Kelvin. Right? So it's the amount of energy in joules required to raise the temperature of 1 gram of that substance by 1 degree Celsius or 1 degree Kelvin. So it's joules per gram times Kelvin. Does that make sense? And for water, the value is 4.18. You should know that. It's in your data sheet, but I would commit it to memory to save time. Okay. And finally, T is a temperature change. Now, let's go up to the earlier reaction. Now, this reaction here is everything to do with the body of water. I want you to remember that. Q equals MCAT is all about the water. Is everyone with me? Whereas the N value here, do you see this N here? It has everything to do with the actual reaction that is going on inside of the water. N is the number of moles of product you produce. Okay? That's what N is. And so you can use this reaction to thus find the energy change per mole of substance produced. Does that make sense? That is how we determine enthalpy changes. Good. Now, who's learnt molar enthalpy of neutralization at school? Okay, well, we'll describe it. So I'm actually not going to show you the definition. You're going to intuitively derive it. Okay? Molar enthalpy of neutralization. Well, what did we say enthalpy was, Gerald?
That's the heat energy within the system.
Good, right? So if we're looking at enthalpy of neutralization, we're measuring the energy of neutralization, and it's molar. So what does that mean? It's per mole. And what is the one product? You looked at the net ionic equation of neutralization. What is the one product that's always formed?
Water.
Good. So the molar enthalpy of neutralization is the enthalpy change in a neutralization reaction when exactly 1 mole of water is formed. Now, in general lab settings, what would the pressure and temperature be? Because you got to standardize this, right? You could get a different molar enthalpy if you're doing it in the Antarctic or whether you're doing it in, Uluru. So what's the typical temperature and pressure in a lab?
25 degrees Celsius and 100 kilopascals.
Exactly. Room temperature pressure conditions. So that is the literal word for word definition. Have a look at this. The energy in kilojoules per mole liberated per mole of water in RTP, room temperature and pressure. Now, what did I say that number typically was when we did our net ionic equation question? It's typically negative 57. Okay, so typically enthalpy of neutralization is negative 57 kilojoules per mole. And that is because all acid-base reactions have the same net ionic equation. Now, I want to stress this. This negative 57 happens when you have a strong acid, strong base. So if you have a strong acid, weak base, you will liberate less energy than this. Okay, and that is to do with the bonds in that weak base. So remember, if you ever have a weak acid or weak base, it's going to lower this enthalpy change. Everyone with me? So let me give you a thought experiment. This is how they test you in an exam question. If a student spilled concentrated sulfuric acid in the classroom, what would be an appropriate base to neutralize that spill? And why? Pick any base. You have freedom of choice. Would you pick a strong base like sodium hydroxide, or would you pick a weak base like sodium carbonate?
Strong base.
If you pick a strong base, okay, and what about you, Gerald?
Weak base.
Okay. Now, Gerald, why would you pick a weak base?
Because you would ideally want to decrease the Actually, wait, can I change my answer?
Are you sure you want to? Explain your original thought. You want to
originally it was because you would want to probably decrease damage to surroundings by decreasing change in enthalpy or the heat which is produced. So you would use the weak base.
You're completely right, actually, right? So you need to understand this. Even with a strong acid, strong base, or a weak acid, strong base. So imagine we had HCl, which is a strong acid, and it combines with a weak base like sodium carbonate. The reaction will always go to completion. You never form an equilibrium. I want you to remember this. All neutralizations go to completion. So we don't care about how strong the acid or base is. What we care about now is the enthalpy. I told you it's highly exothermic. So if we were to put sodium hydroxide on the hydrochloric acid, that would cause extreme amounts of heat release. In fact, you could get boiling of the solution, right? And that would be a whole other additional danger to the classroom setting. Does that make sense? The other reason we actually prefer to use sodium carbonate is because this comes as a solid. It looks like sand, right? You've seen baking soda before, right? So sodium carbonate has a similar solid composition, so it can actually absorb the liquid of the acid as well, and thus limit the spread of the acid physically. So that's why we prefer to use a weak base that is a solid over a strong base in chemical spills. And this question has come up before, so that's why it's hard to understand that. All right, are we ready to start doing some exam questions? All right, so I'm going to throw you in the deep end. Here's your first question. Joe, how about you?
I've got an answer, but I'm a bit suspect about the way I went to that. So yeah.
Okay, what's your answer? What's the final answer?
I got 25.75 degrees Celsius.
Okay. Okay. How many sig figs is in the question though?
3.
Is it 3? What's the lowest figs you see?
Mine is 57.2.
What about 0.1? Potassium hydroxide.
Right.
Make sure your answer is always to the correct sig figs, because there'll always be one question in the HSC that they mark sig figs on, and if you don't do it right for that one question, you'll lose a mark. 1 mark is big in the HSC. 1 mark drops you down thousands of ranks, and you're you can go from a state rank to a mid-band 6 in 1 single mark. So that's why it's so important. Okay, let's start going through it. So we'll start with you, Gerald. What's the first thing I should do?
First thing I did was calculate the number of moles of potassium.
What's the first?
Right equation, right?
Yeah. So what is the equation?
KOH plus HCl, and that gives you H2O plus KCl.
Good. All right. Balanced or not balanced?
That's balanced. So.
Okay. So now tell me, what data do we have?
So you have the volume and concentration of potassium hydroxide.
Good. I want you to say C and V. Give it to me mathematically. So C of KOH is
equal to 0.1 molar.
Okay. And what about V of KOH? And
that is equal to 27.9 milliliters.
Okay, done. So that's C and V. What about HCl?
C of HCl is equal to 0.11 molar.
Okay, and what's V of HCl?
And V of HCl is equal to 31.25 milliliters.
Okay, what else do we have? What are the data?
And then we also have the initial temperature.
Okay, and let's say I'm stuck now. What should I do?
As in, like, what's the next step?
Yeah.
So I calculated number of moles of potassium hydroxide and HCl.
Good, sure, that works out. But what you could also do is draw a diagram if you'd like, and then, like I said, frame the question. What is it actually asking? It's asking for TF equals to question mark. Does that make sense? Yeah. So if we want to find TF, we've got TI. We need to find change in T. So the true question is, what is the change in temperature? If you find change in T, you've got your answer, right? That's what I mean by framing the question. Good. So number of moles of KOH, what did you get? Restart your turn. So tell me, for N of KOH, N of HCl, what did you get?
For N of KOH, I got 0.00279 moles. And for HCl, I got 0.003437 moles.
Joe, did you get the same?
Yeah, that's right.
Okay, so why did we find the number of moles of each? Restart? What are we trying to do now?
We're trying to find which one is the limiting reagent to find out how much of it is actually used up.
Good. Okay. Yeah. Right. Why do we care about the limiting reagent, Gerald? What's the end goal of all this limiting reagent work?
Because we want to find out number of moles of H2O produced.
Very good, right? Because that's our n value. If you remember the equation, triangle H equals negative Q and N. Well, we've got triangle H. Did you all see that? So I'll write that as well. Triangle H equals negative 57.2 kilojoules per mole. So you got triangle H. If we can use limiting excess to find N, we can find Q. And we've got all the other data, so we can thus find change in T. So the approach is actually quite straightforward. So now it's just about following through. So good. So the limiting reagent would be KOH, right? Now, Risa, how do you find the number of moles of water?
Use the stoichiometry so that you know that then the number of moles of H2O is also the number of moles of KOH, which is
So I store that as A and store this as B. So yeah, that's going to be equal to A moles. Yeah. Very good. So now we can use triangle H equals negative Q and N, and we can find Q. Q equals to triangle H times N, or negative triangle H. So this is going to be negative of negative 57.2 kilojoules, because remember it's always exothermic per mole, times A moles. Now, do you see I'm writing units here? I don't usually do that, but the reason I'm doing that is because triangle H is always in kilojoules per mole, whereas when you use Q, you must convert it to joules per mole. Okay? That is why units is very important. So always be cautious of that. It's a huge silly mistake students make, going from joules to kilojoules. So What's our answer for Q? Tell me the answer in kilojoules and joules, Gerald.
So in kilojoules, I got minus 0.159588.
So minus
0.159588.
Okay, let's store that as
Shouldn't it be plus here because it's
it should be. It's minus of minus, so it should be plus.
Oh, yeah.
Remember, Q is the energy absorbed by the water. If it's an exothermic reaction, think about it. Where did all that heat go? To the water from the system. So it has to be plus. And mathematically, it makes sense because it's an exothermic reaction and Q is negative. Negative of an exothermic or negative value is positive. Does that make sense? Good. So that's our kilojoules, but let's convert it to joules. So that's going to be, is it 159.58 joules?
Yeah.
Good. Let's store that as D. All right. Okay, so now we know Q equals to MCAT. What's our mass value? What's a mass of water? Rheostat?
Is it 27.9 plus 31.25, which
Exactly, right? It's all just water. That's what the solution is. So what is that?
59.15 milliliters.
Good. So convert that to liters. And what's the specific heat capacity of water? 4.18. So what's our final answer?
Sorry, I think I. Okay. Yeah.
What did we get?
I got 25.6 degrees Celsius. I mean 0.6 as the change.
Okay, what was the full number?
Hmm?
What was the full number? Was it exactly 0.6? What's the full number?
Oh, full number was, well, it was long. It was like 0.6454. Yeah.
Okay, good. So round that off to X. Good. And the final thing we can say is, well, we know that change in T is equal to TF minus TI. We're trying to find TF. So TF is change in T plus TI. So the answer is equals to 25.645. You said 25.7. Is that because you rounded it, but it wouldn't round up? What
Yeah,
made you...
I got 25.75.
I think it's 645. I think the last time I'd done this question, it was 0.645. Double check your working.
Yeah. I think I might have rounded a bit too early somewhere.
Yeah, never round in chemistry until the very end. You want to make this a constant practice. Never ever round. Always store it, and at the very end, you then round it. Okay? Because they can mark you down, even if you're off by the decimal points. So good. So then this will round off to final temperature being 30 degrees because it's to 1 sig fig.
If I still got 30 degrees, well, like, yeah, if I still got 30 degrees Celsius, like the significant figures, even if my like unrounded answer was like slightly off, would that be a problem?
It really depends on your marker. See, that's the thing. I think we have to realize that schools are very non-systematic. They do whatever they like, right? So what would happen in that case is if you sat your exam and you did that, and if there was a very small standard deviation in the cohort, then they would make that part of the criteria and you would lose the mark. Okay? So that's typically what happens. In the HSC, they try to be lenient, so they may give it to you, but certain questions it's very strict. It all depends what was made as a marking criteria. So I would say, to be safe, you want to have a perfect answer, round it off at the very end. Okay? Good. All right, good job. Homework is going to be, you should have access to this booklet. I will double check your access. If you don't have access throughout mid next week, do message me, okay? And I'll follow through on that for us. So page 20, 21, 22 are all additional practice questions of the same type. So you can do that in your own time, okay? If you can do those questions, it's very easy. And I guess the one thing we'll talk about, discrepancy between theoretical and lab values. So Risa, what would the main discrepancy be here? What would result in a discrepancy between the true value and our calculated value for enthalpy change? What is the main source of error in this experiment? Come on, there's a reason we use double styrofoam cups.
Energy released into the surroundings.
Exactly, right? And that results in a lower Q value than in theory, right? Because it's
sorry, my parents are here and they just need me to open the door, so I'll just.
Okay, no worries. Okay, so yeah, so that's what I'm mentioning. The main issue here is heat loss to the surroundings. Heat loss. Okay, Gerald, how would you improve this experiment to prevent the heat loss? We would be double insulated. So what else could we do?
Use less reactants such that the change in temperature isn't great, so you won't lose as much heat to the environment.
Change in temperature is not so great that you will not. But see, the when we talk about accuracy, it's about percentage error, right? So the percentage error will still be there, even if the temperature change is larger. I get where you're coming from. I would say if you used more reagent, you'd cause more heat change. I think that's good, because if you think about this, if you use a very tiny amount of reagent, what if your thermometer can't even pick up the temperature change accurately? That's the limiting factor, right? If the temperature change is 0.0002 degrees Celsius, your thermometer won't even pick up a temperature change, and thus you'll be limited by the accuracy of your instruments. So I would say you'd want a noticeable temperature change so you can actually pick it up accurately on a thermometer. But good thought, but I would say one of the main things is heat shields. So you could use certain structures like aluminium that can reflect heat back into the system. But again, it's a bit wishy-washy. It doesn't work too well. Good. Let's move on.